Well, hello there. We're going to do chapter 31, the possibility of a quote unquote finite and yet unbounded universe. And that's the universe that I can see is curving on itself as an idea, uh, like a donut or something. But so we will go ahead and read through this. This chapter 31 is just maybe like 5 pages long. It does have some equations, so if you got a math allergy, close your eyes. Don't let it scare you. Let's see, here's an equation, and got a potential divide by zero there. Or we'll see what happens. Um, so here we go. Let's see what Einstein has to say. Chapter 31, possibility of a finite and yet unbounded universe. But specifications on the structure of the universe also move in quite another direction. The development of non-Euclidean geometry led to the recognition of the fact that we can cast doubt on the infiniteness of our space without coming into conflict with the laws of thought or with experience. Riemann, Helmholtz. These questions have already been treated in detail and with unsurpassable lucidity by Helmholtz and Poincare, whereas I can only touch on them briefly here. So if you want to learn more, you can go to those guys. Uh, But yeah, time is so finite, so you have to kind of choose what pathway through the jungle you want to go through. And yeah, I'm just carving a little path here. Okay, so next next paragraph. In the first place, we imagine existence in two-dimensional space, flat beings with a flat. I was talking about flat Earth in the last video. Well, now we're talking about flat beings with a flat implements, and in particular flat rigid measuring rods, like flat Earth people, and are free to move in a plane. Okay, so this is a plane. Um, for them, nothing exists outside of this plane. That which they observe to happen to themselves and to their flat things is the all exclusive reality of their plane. So this is like all of us in this little piece of paper, flat plane, all billions of people just hanging out on a small square. Flat things is all exclusive reality in their place. In particular, the construction of the plane Euclidean geometry can be carried out by means of the rods. As an example, the latest construction considered in chapter 24, in contrast to ours, the universe of these beings is two-dimensional, but like ours, it extends to infinity. Okay, so what is that like this? So you take a little piece of paper and see if we can just kind of roll it somehow, like this. There you go. So then you're like walking along and walking along, just like Earth is kind of. In their universe, there's room for an infinite number of identical squares. Okay, this is like in between, made up of rods. To say its volume surface is infinite. Okay, if these beings say their universe is plane, quote unquote plane, there is sense in the statement because they mean that they can perform the constructions of plane Euclidean geometry with their rods. These are measuring rods. In this connection, the individual rods always represent the same distance independently of their position. Let us consider now a second two-dimensional existence, this time on a spherical surface instead of on a plane. The flat beams with the measuring rods and other objects fit exactly on the surface and they are unable to leave it. The whole universe of observation extends exclusively over the surface of the sphere. Are these beings able to regard the geometry of their universe as being plane geometry in their rods? With all its realization of quote unquote distance, they cannot do this, for if they attempt to realize a straight line, they will obtain a curve, which we quote three-dimensional beings unquote designate as a great circle, like around the Earth, to say a self-contained line of definite finite length, which can be measured up by means of a measuring rod. Similarly, this universe has a finite area that can be compared with the area of a square construction with rods. The great charm resulting from this consideration lies in the recognition of the fact that the universe of these beings is finite and yet has no limits. Okay, but the spherical surface beings do not need to go on a world tour in order to perceive that they are not living in the Euclidean universe. They can convince themselves of this on every part of their world, provided they do not use too small a piece of it. Starting from a point, they draw straight lines, arcs, or circles as judged in three-dimensional space of equal length in all directions. They will call the line joining the free ends of these lines a circle. For a plane surface, the ratio of the circumference of a circle to its diameter, both lengths being measured with the same rod, is, according to Euclidean geometry of the plane, equal to the constant value pi. If you know, pi is not like apple pie, cherry pie, pumpkin pie. uh, so which is independent of the diameter of the circle. On their spherical surface, our flat beings would find for this ratio the value sine of r over big R times pi divided by r over big R to say a smaller value than pi. The difference being the more considerable, the greater is the radius of the circle in comparison with the radius r of the world, quote unquote, world sphere. By means of this relation, the spherical beings can determine the radius of their universe, quote, world, unquote, even when only a relative small part of the world sphere is available for their measurements. But if this part is very small indeed, they will no longer be able to demonstrate that they are on a spherical, quote, world, unquote, and not on a Euclidean plane, for a small part of the spherical surface differs only slightly from a piece of a plane of the same size. Thus, if the spherical surface beings are living on a planet of which the solar system occupies only a negligible small part of the spherical universe, they have no means of determining whether they are living in a finite or an infinite universe, because the piece of universe, quote unquote, to which they have access is in both cases practically plane or Euclidean. It follows directly from this discussion that the sphere beings, the circumference of a circle first increases with the radius until the, quote, circumference of the universe, unquote, is reached, and that it thenceforward gradually decreases to zero for still further increasing values of the radius. During this process, the area of the circle continues to increase more and more until finally it becomes equal to the total of the whole, quote, world sphere, unquote. Perhaps the reader will wonder why we have placed our, quote, beings, unquote, on a sphere rather than another closed surface. But this choice has its justification in the fact that of all closed surfaces, the sphere is unique in possessing the property that all points on it are equivalent. I admit the ratio of the circumference c of a circle to its radius r depends on r, but for a value of r, it is the same for all points of the, quote, world space, unquote. In other words, the, quote, world space, unquote, is a, quote, surface of the constant curvature, unquote. To this two-dimensional sphere universe, there is a three-dimensional analogy, namely a three-dimensional spherical space, which was discovered by Riemann. Its points are likewise all equivalent. It possesses a finite volume, which is determined by its radius 2 pi squared r cubed. Is it possible to imagine a spherical space? To imagine a space means nothing else than what we imagine an epitome of our, quote, space, unquote, experience. To say of experience that we can have in the movement of, quote, rigid, unquote, bodies, in this sense we can imagine a spherical space. Suppose we draw lines or stretch strings in all directions from a point and mark off from each of these the distance r with a measuring rod. All the free endpoints of these lengths lie in a spherical surface. We can especially measure up the area f of this surface by means of a square made up of measuring rods. If the universe is Euclidean, then f equals 4 pi r squared. If it is spherical, then f is always less than 4 pi r squared, with increasing values of r, f increase from 0 up to a maximum value, which is determined by the quote world radius unquote. But for still further increasing values of r, the area gradually diminishes to 0. At first, the straight lines which radiate from the starting point diverge farther and farther from one another, but later they approach each other, and finally they run together again at a quote counterpoint unquote to the starting point. Under such conditions, they have traversed the whole spherical space. It is easily seen that the three-dimensional spherical space is quite analogous to the two-dimensional spherical space. It is finite, to say, of finite volume, and has no bounds. It may be mentioned there's yet another kind of curved space, quote, elliptical space, unquote. It can be regarded as a curved space in which the two, quote, counterpoints, unquote, are identical, indistinguishable from each other. An elliptical universe can thus be considered to some extent as a curved universe possessing central symmetry. It follows from what has been said that closed spaces without limits are conceivable. From almost these, the spherical space and the elliptical excels in its simplicity, since all points on it are equivalent. As a result of this discussion, a most interesting question arises for astronomers and physicists, and that is whether the universe in which we live is infinite or whether it is finite in the manner of the spherical universe. Our experience is far from being sufficient to enable us to answer this question, but the general theory of relativity permits of our answering it with a moderate degree of certainty, and in this connection, the difficulty mentioned in chapter 30 finds its solution. Okay, so that's the end of this chapter. Next chapter is 32, the structure of space according to the general theory of relativity. And so that's pretty interesting. Yeah, so I don't know, maybe the universe is kind of like our Earth in a sense. When you go a long ways, you end up back where you started from in the same direction. Maybe the universe has some similar property. And then maybe you can even go outside that quote unquote universe by moving in a weird rocket ship or something. Who knows? No idea. But it's pretty fascinating stuff he talks about, and hope you enjoyed it. I hope you learned something, and I'll see you later.